Hello everybody, welcome back to another Gregorious Math video. In this video I'm going to be going over I guess you could say it's coronavirus related probability problem that my friend Sloba set me, and it's a typical example of how to use Bayes' theorem. This is a more interesting probability question because it's much harder to use common sense to just solve it. Like there's as opposed to the probability problems like there are 8 boys and 9 girls. What's the probability that if I pick randomly I'll pick a boy? This is actually like getting into the more interesting probability. And yeah, it's I guess you could say it's coronavirus related. So there's a population, there's a disease, right? There is an illness, alright? And which shows where that's just for context, let's say where people who have it don't show symptoms for a while. Alright, so the government has the whole population tested. So the whole population is tested. Okay, and the results are the following. So for a healthy person, for healthy people, it is correct 97% of the time. So 3% of healthy people get false results, like they're false positive results, and ill people get correct results 98% of the time. And I forgot to mention that 1% of the population is genuinely ill, is ill. Right? So this is the problem, and so this is the context, and the problem is, what is the probability? I'll write it in red so that, if you're glancing at the problem again, you know exactly what the question is. What is probability that if you get a positive test, you are actually ill. Alright, that's the problem. Now, this is actually quite a counterintuitive problem, because you would think that it's going to be quite high, somewhere near 90%, because for ill people, it works 98% of the time, and for healthy people, it only fails 3% of the time, so it should be quite high. But the thing is, 1% of the population is ill, so this 98%, even though it's a much larger number, it might not actually be as big as the 3% of healthy people that test positive. So how should we approach this? Well, Bayes' theorem, I won't prove it, I think that 3 blue 1 brown has a more intuitive explanation of Bayes' theorem. This is more an example of it, and it's essence of probability series. I would recommend that video, and I'm sure that you can find a proof somewhere. But what it says is the probability of A, given that B has happened, so when B is true, the probability of A is equal to the probability of B when A is true times the probability of A divided by the probability of B. And we're going to find out, so if A is you're ill and B is you get positive test results, then what we want to find is P of A when B is true. And so we can apply Bayes' theorem, because it turns out when we break down the problem, we actually have all of this information right here. So let's do this. It's quite a wordy problem, so it's quite intimidating, but once you break it down, it's not too bad. So A is the number of people... Sorry, not the number. Sorry, it's just you are ill. B is positive test results. Alright, let's get P of A. So the probability that you're ill, given to us right here, is 1%, so 0.01. P of B, so the probability that you get a positive test result, well, that is 0.98 times 0.01, because that's the actual amount of people that are being tested, plus the wrong test results, which is 0.03, because that's the percentage that get wrong test results, times 0.97, because that's the percentage of people that are healthy. So this right here is the 3% of the healthy people. And now if I grab a calculator, one sec guys, should come out to be, yeah, 0.0395, what it should come out to be. And so, the probability that you get a positive test result when you're ill is 0.098. So, look, we have this, we have this, we have this. Now we're ready to find the probability that you get a positive test, that you are ill, given that you have a positive test result. So let's do this. Let's just find it out. I'll do it in red, because this is the final solution. So, overall, the probability that when you get a positive test result, you are actually ill, is equal to, let's just write it out one more time. And this is equal to, well, what's this? This is of the probability that you get a positive test result given that you're ill is 0.98. Sorry, I'm not sure why I put a 0 there. 0.98 because it's probably given that you're ill, yeah, 98% of the time, yeah, 0.098 times 0.01, which is the probability that you're ill, over this 0.0395. And this is approximately, this will come out to be 24.8 something something. This is approximately 25%. Now that is very, very counterintuitive. Because surely it should be something like really high, like, I don't know, 90% or 80% even. Now, let me show you an example which I found illuminating, because I was confused by this too. I mean, I looked through all the steps, they looked right, so I decided to just do an example. So, with 10,000 people. Alright, so, now, the population that are ill, 100 people are ill. Right, because that's 1% of 10,000. So that means that 9,900 people aren't ill. Alright, so now, so you get, if you're ill, you are ill, let's just write it as P of B, A, because that's much more concise notation. So B and A are still, A is you're ill and B is you get positive test results. It's just 0.98 or 98 people. Alright, so the probability, so 98 people, sorry, not the probability. So the probability is 0.98, which equates to 98 people getting positive test results when they're ill. And then the probability that you get a false test result is going to be 3%, so 3 over 100 times 9,900 is 297 people get false positive tests. Wow. So that's much more than 98, right? And so the probability that you're actually ill, now this is an easy, so this becomes an easy probability question now, because I have 297 who get false test results, 98 who do, who get actual test results. What's the probability that they're going to get actual test results? And that's clearly going to be 98 over 395, because that's this plus this. And this actually turns out to be exactly the same. It's approximately 25%. Right, because when you just multiply both the top and bottom by like, I don't know, like a few thousand, maybe 10,000, maybe 1,000. No, it's much more than 1,000. When you multiply the top and bottom by like 100,000 or so, I can't be able to figure it out exactly, you're going to get this. And this is again approximately 25%. So yeah, that is actually very counterintuitive, and it's at this point where probability and common sense, it's harder to solve much harder to solve probability problems with just common sense, and where theorems like Bayes' theorem, this is like a really fundamental theorem in probability, come in super handy. So yeah, that's it for today. Thank you guys for watching, and yeah, I'll see you in the next video. Bye.